I just talked about that. You weren't listening. I'm going to give you an extra day if you want to, or you can turn it in now. An extra day from what you just learned. Maybe that can help you some from what I just explained. Okay?
What chapter is this? 44?
We're in chapter 44. We're on page 842. We don't have any page numbers on this page.
Is it 44.2?
Okay. We talked last time. We were talking about 3 different lifespans, 3 different life histories. These are called survivorship curves. Survivorship curves. You have type 1 organisms, type 2 organisms, and type 3 organisms. A type 1 organism usually lives a long time and then dies at old age. That's like us. Y'all are type 1 organisms. Most people live long and then die when they're old.
Does that depend where you live?
Well, in some places there's death at young, but for the most part, for just human population as a whole. Some organisms don't live like that. Some organisms, most of them die at a very young age, like mosquitoes or roaches.
That'd be type 2?
That would be type 3. Type 3, death comes early on. So almost all the creatures die early, but a few live to be old. And then type 2, death is really not related to age. Some die young, some die old.
Does that mean they live really long?
Not necessarily.
Or they just die a lot?
This is the bottom is percent of lifespan. So type 1 creatures, they might not live very long, but most of them die at the end of their lifespan. Type 3 creatures, most of them die at the beginning of their lifespan. It's saying nothing about how long the lifespan is.
So that means they pretty much die through unnatural means, like?
Not necessarily. Could be natural. But could be naturally they die at a young age. But it's just, this is a very general thing. It's not saying anything specific about any creature. Mosquitoes lay a whole bunch of eggs, and most of the mosquito eggs are eaten by predators, and so most of them die very young. A few make it all the way. So mosquitoes looks just like a type 3. Turns out bluegrass, most of them live kind of a long time and then die toward the end. So bluegrass is an example of a type 1.
Which chapter is it?
Chapter 44, page 842. Take a look at this.
The most fundamental mathematical expression of growth. Population size increases exponentially with time. The term R is the growth rate of the population. In reality, no matter how rapidly a population grows, it eventually reaches a limit imposed by shortages of environmental factors such as light, water, space, or nutrients. A population may stabilize at a certain size, called the carrying capacity. The carrying capacity, K, is the maximum number of individuals that the environment can support, while R is the growth rate of the population.
Okay, let me talk about this a little bit. If we take a single bacterium and we put it on a little plate, do y'all know how bacteria multiply? What the name of the process is?
Fission.
Binary fission. Bacteria divide in 2. And so if you start with 1 bacteria, after 1 generation you have 2 bacteria. Each of those divide and you have 4. Then 8, 16, 32, 64, 128, 256. I could keep going, you know. 512, 1024, 2048, 4096, 8192, 16384, 32,768, 65,536. Doing the math in my head here. They tend to get math in 1986. Anyway, here's generation 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 generations, we have gone from 1 bacterium to 256 bacterium. We call this exponential growth. And that's what you see at the beginning of this graph. It starts very low, but very quickly the numbers in a population can go up. Y'all are familiar in math with exponential growth, right?
Kind of. Whatever.
Logarithmic growth, kind of just takes off. And so, populations will do this. If you just release a couple of rabbits into a field that has plenty of food and no predators, they'll mate. And after start with 2 rabbits, and then all of a sudden you have 15 rabbits. And then each of those are mating, and then all of a sudden you have 400 rabbits. And there's a field full of rabbits. But what's going to happen after a while?
They run out of sources to eat and stuff.
They run out of food. They run out of space. Hawk flies along, and he looks down, and there's 1,000 rabbits down there. He's going to feast, right? And all his hawk friends are going to come around too. And pretty soon, those numbers of rabbits are going to start going down, or at least leveling off. And so that's what we see. This red line is the theoretical growth. Is what the population could do if given plenty of resources and no predators, no disease or anything like that. But in reality, what happens is the population has some limiting factors that limit its growth rate, like the amount of food and predators and disease and stuff like that. And so the actual growth rate looks like this. We call this theoretical growth curve a J-shaped curve, because it's shaped like the letter J. And we call this actual growth curve an S-shaped curve, because it's shaped like the letter S. And so the population is growing very quickly here, and then starts to level off, and then it reaches some point that we call the carrying capacity, which is usually denoted by the letter K. And the carrying capacity is the most organisms that this area can hold, with population size being here on this side of the graph, and time being on the bottom. So as time goes by, the populations will go up and then level off at the carrying capacity. If you chart the human population on Earth, it looks exactly like this. It started out very low. For millions of years, there were just cavemen running around, or hundreds of thousands of years. And then it went up real fast, especially when all the agriculture was invented and medicine. But now it's just starting to level off. We're actually right about in this phase right here in human population. It's starting to do this because we're running out of resources. There's not enough food on the planet to feed everybody. Disease is starting to spread. There's not enough places to put our waste products. And so the population just cannot go up forever. It's got to level off. And they think the human population will probably level off at some point in the next 100 or a couple hundred years. Might take longer than that. It depends. Our technology can invent new ways to grow more food and make more space. If we can fly people off to Mars and live there, then we got more space. And so, build taller buildings, you get more space. So it's interesting how population growth is.
So is human population growth?
Look at all these happy humans. Yeah, it was exponential to a point, and now it was doing this J-shaped thing for a while, but it started to level off a bit.
Well, it doesn't matter how many kids they have. Like, they have only 2 kids versus 12 kids.
If they have 2 kids versus 12 kids, the shape of the J is different. It's a kind of a lower J than a faster rising J.
That's another of the population controls, more birth control and having less kids.
That's right. Birth control tends to make the growth level out. Yeah.
Is that a good thing or a bad thing?
It's a good thing if we all want to eat and live. We can't overrun ourselves with. Look at this. Look at all those mice. This is probably not too good. I don't know what they're talking about here, but anyway.
Really about that?
Mice reproducing quickly?
No, the behavior thing. The picture of that mouse.
What was
when
it
the
doing?
mom was like with the children. It's like
Oh.
a special like protein or something.
Yeah, they take away the protein and she doesn't take care of her kids. That's interesting. So that means that maternal care is genetic. To some extent, yeah. Okay, so the next thing you need to do is you need to be able to read this type of graph. This is called an age structure diagram, and you're likely to see one on the AP exam. Are you with me, Steph? So these graphs, this graph on the left and this graph on the right have different looks. The graph on the left is an increasing population. It's shaped like a triangle here, a pyramid. The left side is male, and the right side is female. Y'all see this? Sarah, are you with me here?
Yeah.
Okay.
The left side's what?
The left side, see that symbol? That's the male symbol. That's what Austin Powers wears. And the right side is female. And the bottom of the graph here is pre-reproductive ages. That's the kids in the population. The middle of the graph are the reproductive ages. That's when you are able to have kids, the adults. And the post-reproductive is up top. That's the old people in the population. And if you notice in this graph, there's more kids than anything. That's typical of a population where they're having a lot of kids. In a human population, it might be a place like India or Mexico or Africa where there's a lot of kids. Each couple has more than, if each couple, 2 people, have more than 2 kids, then the bottom of the graph is going to be wider than the middle of the graph. Does that make sense? Most countries are like that. Developing countries usually have a greater population of kids because they're having a lot of kids. Even the United States is like that a little bit, but not as much as places like India and Africa.
China's not like that, right?
China is more like this now, or is starting to become like this, because they introduced some laws that tell people they can't have very many kids, and so if the reproductive population is not having many kids, then the kid squares are going to be smaller than the adult squares.
I think the rule is that if you have more than 1 kid, you pay a lot
Pay
of money.
taxes.
You
Yeah,
pay a lot of money.
yeah. You're going to be poor, so not a lot of people do that, and that's a way they had to control their population. It was getting out of hand.
Do you think
So,
America will ever do that?
what's that?
Do you think America will ever do that?
Well, America isn't growing that as fast as countries like that, so that's kind of a big step. I don't know. That's more like a political discussion,
I
really.
think it's if you have more boys, then you can have more boys, but if you have a girl, then you can't have more kids.
Ah,
Yeah.
because the boys can't have the kids, the girls have the kids. That makes sense.
That's why there's a lot of orphans in China.
Yeah.
Orphanages are overwhelmed.
Our pack, yeah. So it becomes a political discussion, but you have to remember, in biology, we're not just talking about humans. They can use these applied to any type of organism. They might say, the marsupials in Australia have an age structure diagram that looks like this, and then ask you questions about it. I don't know. So, but anyway, you can see So we got increasing on the left, a decreasing population on the right, and a stable population in the middle where the adults are having, each couple is having about 2 kids apiece. The bottom square and the middle squares will be about the same size. Does that make sense?
Yep.
Okay.
Why do they show a side for like a male and female when it's
It's kind of interesting when you look at it. For instance, at the top of the graph, do you see that the female square is wider than the male square? It happens on each one of them. Do you notice that? Why is that?
Females live longer.
That's right. Women live longer than men. Did y'all know that? The average age for women is about 4 years longer than men. And so, because there are differences like that, they'll often break it up into women and men. This would also show you, for instance, if there's more boys being born than girls for some reason. You could look at the bottom.
So in China, it'd be like a lot bigger for the males.
In China, the male side would be a lot bigger than the female side.
I think about 10 years from now, that'll be a problem, right?
Probably so.
Won't be.
You'll have a lot of guys and not many girls around, and then you probably, I don't know, probably be tough to find a girl. Might be guys leaving the country to find women. Okay, so they get into some math, and we're not going to go into this math and have you do problems because they haven't asked statistical math questions on populations. Not more than they just don't get into it that much in this. But if you ever take a biological statistics class, you'll get into these equations and such. But the R value, I talked about this before. If you see the R value, that's the rate of population growth. This R value 2.4 basically means the population is growing 2.4 times per generation. So each organism is replacing itself with 2.4 kids. Now you can't have 2.4 kids. It's an average, you see. Some have 2, some have 3. It averages out to 2.4. So every generation is replacing itself, is more than doubling itself if the R value is 2.4. In human populations, you don't see R values that high. But if they talk about an R value being 5 or 6 versus an R value of being 2, the R value at 5 or 6 is going to go up a lot faster than a lower R value.
So when it's going up, what does that mean?
That means the population is growing.
So higher R value equals?
Higher value equals faster growth. And an R value of 1 means the population isn't growing at all because you're just replacing yourself with one organism. And if the R value is less than 1, the population will be dropping. So 1 is the magic number.
So 1 doesn't change.
1 doesn't change, that's correct. And so, and again, the letter K means the carrying capacity. Why they use K for carrying capacity, I'm not sure. There's got to be a reason for it. Why not use C? C must be something else.
Speed of light.
K is like the constant.
But if you ever hear them talk about the K, it's the carrying capacity. So here's this S-shaped curve. Let's see some video footage on the S-shaped curve.
Populations may follow an S-shaped curve. There is an initial slow growth phase, a period of exponential growth, and a plateau where the number of organisms the environment can support is reached.
Now this is interesting. It shows in this graph a little going up and down, above and below the carrying capacity. You will see this in populations. It won't stay right at the carrying capacity. you'll have something happen where some of the individuals die. And when the population is below the carrying capacity, now there's plenty of food for everyone. Times are good. So they'll have a lot of babies and the population will go up. And when the population gets above the carrying capacity, now there's not enough food for everyone, so times are bad. So it'll drop back down. And so you'll see this wavering above and below the carrying capacity as the population changes.
What's it when it first starts out? Lag?
That's just kind of a lag phase is what they call it, kind of a slower growth phase.
And then
The organisms are multiplying, but you don't see the numbers on the graph start to rise rapidly until a little bit later.
Most large, long-lived organisms grow in S-shaped curves. With plenty of food and living space, the population size doubles in the typical J pattern. But as more organisms appear, they must compete against each other for limited resources. In time, the population stabilizes at a level the environment can sustain, what scientists call the carrying capacity. If the availability of resources changes, the carrying capacity also changes. In nature, resources act as the limiting factors which control population growth.
Okay, so all of a sudden this population went down here. And that's because one of the limiting factors changed. For instance, this area could supply a certain amount of food. But what if something in the area changed? Like what if there was a drought where you couldn't supply that much food? Then the carrying capacity is going to go down and the population will follow it. So carrying capacities aren't set in stone. They can change. They can move based on these limiting factors like food or amount of water or amount of sunlight or all sorts of things. Skipping through the math. Look what happened to these reindeer. They were released onto an island outside some island in Canada or off the coast of Alaska or somewhere. I think it says St. Paul Island, Alaska. This was an Alaskan island. Somebody brought reindeer over there, and the number of reindeer went up. Can you see that's an S-shaped growth curve, almost exactly. It's never going to be perfectly smooth, like the textbook example, but very close. And then it reached a point, and all of a sudden, see, these reindeer, they eat lichens. And lichens are real slow-growing creatures. So they reached a point in 1935 where they ate all the lichens. There weren't any lichens left, and then bam, the population crashed. And there's none left there now. Isn't that crazy?
What are lichens?
Lichens are little fungus living with an algae. You see it growing on the barks of trees. You know that kind of crusty white stuff?
Yeah.
Those are lichens. And lichens will live in the ground, and these organisms can smell them out. Now, normally, reindeer will just go somewhere else when they run out of food. But guess what happened in this case? They were on an island. There was nowhere to go. See, reindeers are migratory. They will move from one place to another and give the lichen time to recover, and then come back there many years later and feed again. But the lichen couldn't, they had nowhere to go here, and so they all died out.
There was no Christmas that year.
Can reindeer swim?
Maybe short distances.
Because I don't like deer.
Yeah, I think this was an island kind of far off. And weren't able
You ever
to
seen
live.
Deadliest Catch? They have the island like St. Paul. It's in the middle of the Bering Sea.
Oh,
I
really?
think that's St. Paul.
That's St. Paul?
I think so.
I did not know that.
Double island.
Very cool. Okay, so read sections tonight. 40. Wait, is it? What time is class in?
In a minute.
Yeah, we're out of time. So I got through 44.3, and I couldn't quite start 44.4. But if you could read through 44.5, 20.4. I will talk a little bit more about it next